Hello friends, welcome to this sixth lecture on major theory. Okay, so what we are doing, this is a sixth lecture on major theory. Until now, what we are doing, we have this situation, we are studying the properties of M star. There are three properties of M star. One is translation invariant, and second is countable additivity, subadditivity, and the third is that length of an interval is equal to the outer measure of that interval. So we are going to prove this property in this video. The proof of this property is little lengthy, but it is easy, simple. So let us start with proving that length of an interval, this is the last property for M star, is actually M star of that interval, right? So let us do that. We'll divide our situation in different cases, okay? And we'll cover all the intervals. So, for the first case, we are dealing with closed and bounded interval. Suppose our interval is closed and bounded. Okay, suppose you are having a closed and bounded interval. It means that your interval is of the form a b. Then what is the length of the interval? Length will be b minus a. And what you want to prove? You want to prove that m star of I is b minus a. This is what your aim is in this particular case. Okay, so let us do that. Okay, if we prove that, we know that if you want to prove this equal to this, you can prove that m star of I is greater than equal to b minus a, and m star of I is less than is equal to b minus a. Then it implies that m star of I is equal to b minus a, and this thing proving less than equal to is quite simple. Let us look at that. You have for any epsilon greater than 0, okay, suppose this is a small number, howsoever small, you have your interval like this is your a b, this is closed and bounded interval, and you can take here a point which is a minus epsilon by 2, and here a point which is b plus epsilon by 2. Then for any epsilon greater than 0, a minus epsilon by 2, b plus epsilon by 2, open interval. Okay, this is an open interval which contains your closed interval a comma b. Okay, it means that for any epsilon greater than 0, this a minus epsilon by 2, this collection of intervals which contains only one interval, is an open and bounded cover for your interval a comma b, is an open and bounded cover for the interval a comma b. And by definition, what is m star of a comma b? M star is, you have to take the minimum of the sum of the lengths of all such covers. Therefore, for sure m star of I is less than is equal to sum of the lengths in this collection of the intervals, but here is only one interval, so this is length less than is equal to length of this particular interval a minus epsilon by 2, b plus epsilon by 2. Therefore we have that m star of I is less than is equal to, what is the length? This is b plus epsilon by 2 minus a plus epsilon by 2. So we have m star of I minus b minus a is less than epsilon. Okay, so you have proved that given any positive number epsilon, your this quantity is less than is equal to that positive number. So it means that a quantity which is less than is equal to every positive number is less than is equal to 0. So it implies that m star of I minus b minus a is less than is equal to 0, which implies m star of I is less than is equal to b minus a. So one way we have proved. The only thing is left, which is left, is that we have to prove that m star of I is greater than equal to b minus a. Let us prove that for the first case where we have considered open and bounded intervals. So let us do that. So our aim is now to prove that m star of I, where I is a comma b bounded or closed and bounded, is greater than or equal to b minus a. This is our aim, right? So let us do that. You have to prove this thing. It means that you have to prove that infimum of summation L of I k from 1 to infinity, such that your interval AB is contained in union of k from 1 to infinity, ik open and bounded. This is the definition of m star, open and bounded. They should be greater than equal to b minus a. This is what you have to prove, right? Now if infimum of something is greater than or equal to b minus a, okay, then obviously every quantity in that subset will be greater than or equal to b minus a, right? So in other words, we can prove that summation k from 1 to infinity L of ik is greater than or equal to b minus a whenever AB is contained in union of ik's and ik's are open and bounded. If you can prove that this thing is true, this particular thing is true, then automatically it means that this thing is true, right? So this is what we have to prove. We have to prove that this quantity summation of lik's is greater than or equal to b minus a whenever ab is contained in union of ik's, and that union is countable. Okay, now we have a thing which is called Hein-Borel theorem. Okay, what this theorem says that, I'll write down the statement completely so that we can understand it better. This theorem says that, this Hein-Borel theorem says that let f be any closed and bounded subset of real numbers, set of real numbers, then every open cover of f has a finite subcover. Then every open cover of f has a finite subcover. This theorem will help us in proving this particular thing which we want to prove. What does this mean? It means that whenever your interval AB is contained in union of ik, k from 1 to infinity, and because this is closed and bounded set and this is an open cover, it means that AB is actually contained in union of ik, k from 1 to n. It means that this countable cover will somehow leads to a finite cover. It means that every open cover has a finite subcover. It means that out of these countable intervals there will be only finite intervals which will cover your closed and bounded set. Okay, so proving this thing is equivalent to prove that summation k from 1 to n L of ik is greater than or equal to b minus a whenever AB is contained in union of ik, k from 1 to n and ik open and bounded. Okay, so this is the thing which we have to prove that m star of I is greater than or equal to b minus a. So let us do that, right? So what is our aim now? We have to prove that whenever AB is contained in union of ik, k from 1 to n, right, then m star of summation of these lengths ik, k from 1 to n is greater than or equal to b minus a. If we can prove that, this will automatically imply that m star of I is greater than or equal to b minus a, which is our aim. So let us prove this thing, this particular thing which we have to prove. Okay, let us do it. Okay, so you have AB, you have this thing that AB is contained in union of ik's, right, k from 1 to n. It means that A is contained in union of A is an element of this union. It implies that there exists at least one interval, okay, and these ik's are open and bounded, so I'll denote these intervals as like this ak, bk. So there is at least one interval a1, b1 such that my A is contained in A1, B1. That is A1 is less than A less than B1, right? Okay. So we have starting from here we have two cases, right? Let us change the color. You have these two cases. Either your B1 is greater than or equal to B, or your B1 is less than B, right? So we have this situation. In this case, obviously we have A and B here, and A belongs to the interval A1 B1 and B1 is greater than equal to B. So this is a situation like this, and in this case we have a situation like this, that A is contained in the interval A1 B1 and B is greater than B1, right? So in this interval, in this particular case, you can note that B does not belongs to A1 B1, right? Okay, now see in this case. In this particular case, you have this thing, summation k from 1 to n L of ik, right? And this is a collection of intervals, and a1 b1 is one of the interval. So sum of the lengths of all of the interval is for sure greater than equal to b1 minus a1, right? And you can see that b1 minus a1 is for sure greater than equal to b minus a, which is greater than equal to b minus a. So we have proved in this case that summation k from 1 to n L of ik is greater than equal to b minus a. So in this case we are done, right? So we have this particular case left with us where we have to prove that. So we are having this particular case where we have to prove that summation of L of ik is greater than equal to b minus a, right? Now you can see that in this case b1 belongs to a comma b. Clearly from here you can see b1 belongs to a comma b, and b1 does not belongs to a1 b1 because a1 b1 is an open interval, therefore it is not containing the endpoints of the interval. It means that now b1 is contained in a comma b and a comma b is contained in union of ik's, right? So it means that there is some interval a2 comma b2 such that your b1 belongs to that interval a2 comma b2, right? So it means that, so I'll just make the cases again. We have something like this, a is lying between a1 b1, right? So you had a case like this, b belongs to a1 b1, and in this case we are done, right? Here we had this case that b does not belongs to a1 b1, right? So we have a situation like this, that we have a1 here, a here, b1 here and b here, and in this case we find an interval, find an interval a2 b2 such that your b1 belongs to a2 b2, right? Your b1 belongs to a2 b2. So we have a situation like this, that b1 is lying between b2 and a2, right? So we have a situation like this. You have a here, you have obviously this is a situation, we have a1 here, this is b1 here and b here. We have two cases. One case is if b2 is greater than equal to b, right, which we had here. Okay, here we had that b1 is greater than equal to b, right? So here we have b2 is greater than equal to b. In that case b will belongs to a2 b2, right? And in that case I'll explain the situations which are possible, and the other case is that b2 is less than b. In this case you have something like this, b2 is less than b, so b2 is somewhere here, right? And a2 is obviously less than b1, so a2 will be here. So you have b does not belongs to the interval a2 b2. So in this case you have b does not belongs to a2 b2, right? So we have these two situations. Let us first concentrate on this situation, right? In this particular situation you have a situation like this. I am discussing this case, right? Let us change the color. So you have a situation like this. You have your a here, a1 here, your a here, b1 here and b here, and you are saying that your b2 is greater than equal to b. So it means that your b2 is here. What are the possible choices for a2? a2 is such that you can see that a2 here, you can see that here you can see that a2 is such that a2 is less than b1. So a2 can be here, it can be here, it can be here. So these are the three choices for a2. Let us discuss all the three choices. Suppose your a2 is at the first position here, right? In that case you have something like this: a1 here, a here. Okay, they have three cases. I am discussing this case: a1 here, a here, then you have a2 here, and then you have b1 here, and then you have b here, and then you have b2 here, right? So in this case you have L of I, which is your b minus a, that is less than, you can see that b minus a is clearly less than is equal to b2 minus a1, right? This b2 minus a1, this is equal to b2 minus a2. Okay, this is less than is equal to, this is this b2 minus a1. Now you see b2 minus a2 is this quantity and b1 minus a1 is this quantity. This common area you are calculating two times. So this quantity b2 minus a1 is for sure less than is equal to b2 minus a2 plus b1 minus a1, right? So these are the length, sum of the lengths of the two intervals out of that collection. So this is for sure less than is equal to summation L of ik, k from 1 to n, right? So this is the case when your a2 is situated here. You can similarly prove the same thing when a2 is situated here and a2 is situated here. So it means that in this case, in this particular case, when we are on the left side of the wing, we are done, right? So what is the situation? So let us make a chart. So we have something like this. We are starting with a case that a is lying between b1 a1, right? Then we have this thing that b belongs to a1 b1, right? In this case we are done. And then we have case that b does not belongs to a1 b1. In this case we find an interval a2 b2 such that b belongs to a2 b2. And then we further have a case that your b belongs to a2 b2. In this case we are done, right? And then we have a case where b does not belongs to a2 b2. In that case we will find an interval a3 b3 where b2 belongs to a3 b3. Then again we have a case that b belongs to a3 b3. In this case again you will be done, you can see. And or we have a case b does not belongs to a3 b3, okay, and so on. You can keep on going, right? And from where you are choosing these intervals a1 b1, then a2 b2, then a3 b3, you are choosing these intervals from the collection ik's. These are the intervals ak, bk, and k is varying from 1 to n. So this is a finite collection. So it means that you will end, your case will stop somewhere because you have a finite collection. You cannot keep on going always, right? So let us suppose that, just write it down, because we have a finite collection, we have to stop somewhere, right? Say at kth step, at mth step, right? So we have a situation like this. I'll draw it again. So you have a situation like this. You started with an interval a, which is lying, you started with an interval a1 b1 such that your a lies between a1 and b1. Then you have a case that your b belongs to a1 b1. You are done in this case, you don't have to discuss this thing. Then you have a case that your b does not belongs to a1 b1. In this case you find an interval where b1 belongs to a2 b2, right? And then you have a case that b belongs to a2 b2. In this case again you are done, right? And then you have a case that b does not belongs to a2 b2, and so on. Then you find an interval b3 a3, a3 b3 such that your b2 belongs to a3 b3, and so on. And at some step you will have bk belongs to ak. At some step you have that your b belongs to, at some step means you will be on the left side of the wing, then only your thing will end. So at the some step you will have something like this, that your b belongs to ak bk, right? At this step what will happen, you have something like this, that summation of L of I and ik's k from 1 to n, right? It is greater than equal to it is greater than equal to summation of the lengths L of ik, k from 1 to m. Okay, out of these n intervals you have chosen m intervals, right? Now what is this? This summation is ak, this summation is bk minus ak, this is the length of the kth interval, mth interval, sorry, plus bm minus 1 minus am minus 1 plus so on till the last interval, that is b1 minus a1, right? Now I am writing the same thing as, I think I can write it as m1 minus, sorry, b1 minus am minus bm minus 1 minus am minus 1 minus bm minus 2 and so on, minus a2 minus b1 minus b1. Now can you see that this thing is negative? Why? Because you have chosen your, here your b1 belongs to a2 b2. So basically we have bk belongs to bk plus 1, ak plus 1, bk plus 1, right? So it means that here your bm minus 1 is belonging to am to bm. So when you separate, am is smaller than bm minus 1, so this quantity is negative. Similarly this quantity is negative and so on, all these quantities are negative. So this thing, this quantity is greater than equal to, if I leave these negative quantities, right? So this quantity is greater than equal to bm minus b1. Is that thing clear? Right? So this quantity is greater than equal to b1 minus b1. I am sorry, here we will have a1. Last thing left will be a1, right? Because b1 we have used. So we have, can you see that we have these, this is negative, negative will positive, negative, negative will become positive. So this is a number which is bm minus a1 plus some quantity, and I am leaving that plus quantity. So obviously, for example, 5 plus 4 is for sure greater than equal to 5, right? So because I am excluding this quantity, right? So the same thing I am doing here. So this quantity is greater than equal to bm minus a1. So where we have reached here that summation L of ik, k from 1 to n is greater than equal to bm minus a1, right? Now your bm, we have stopped at the case where b belongs to am bm. This is the stopping criteria. So it means that b is less than bm and greater than am, right? So this quantity is greater than equal to, if I replace this with a smaller quantity, this is greater than equal to b minus a1. And for sure in the beginning you had this thing that your a belongs to a1 b1, right? So it means that this a1 is smaller than a, so this quantity is greater than equal to, if you replace this with a bigger quantity, you are subtracting a bigger quantity, so this is greater than equal to b minus a. Therefore we have proved that summation k from 1 to n L of I k is greater than equal to b minus a, right? So it implies, as I have already explained, that m star of I is greater than equal to b minus a, and already we have proved that m star of I is less than is equal to b minus a. So both these quantities things implies that m star of I is equal to b minus a, hence proved. And this was the case when I was closed and bounded intervals. So let us consider the other cases, right? Now suppose I is not, next case is closed. We assume that I is a bounded interval, okay, bounded interval, but it may be open. Whenever we have a bounded interval, so we have something like this, right? Suppose I is a bounded interval, then given any epsilon greater than 0, I can find two intervals. One is slightly bigger than I and one is slightly smaller than I. Both of these intervals are closed and bounded. Given any epsilon greater than 0, I can find closed and bounded intervals. You can do this, right? J1 and J2 such that length of I is greater than length of J1 plus epsilon, okay, and length of J2 is less than length of I plus epsilon, right? So we have something like this. We have this thing that length of I minus epsilon is greater than length of J1, and length of J2 is less than length of I plus epsilon. It means that what I have done, I have taken the length of my interval and I have subtracted epsilon from that length, and I have chosen J1 such that length of J1 is less than that quantity, and then I have taken the length of my interval I and I have added a small quantity in that length, and then I have chosen my J2 such that the length of J2 is slightly lesser than length of I plus epsilon, right? Now see, we have this thing, length of I minus epsilon is, I'm sorry, here you have to choose, here from here, right, here will be the sign of less than, right? Length of I minus epsilon is less than length of J. So you have this thing, length of I minus epsilon is less than length of J1, right? Now because J1 is closed and bounded, and we have proved that in case of closed and bounded interval, length of interval is same as m star of J1, right? Now you have you have chosen your J1 is slightly smaller than I, so J1 is contained in I is contained in J2, right? So it implies that m star of J1 is less than is equal to m star of I, and it is less than is equal to m star of J2. This is from the monotonicity property of m star, right? So this quantity is less than is equal to m star of I, right? And what is this? This is less than is equal to m star of J2, again from here, right? From here, right? And what is this? M star of J2 is less than length of I plus epsilon. So what we get that m star of I is lying less than L of I plus epsilon and greater than L of I minus epsilon. It implies that minus epsilon less than m star of I minus L of I is less than epsilon. It means that m star of modulus of m star of I minus L of I is less than epsilon, right? So it means that given any positive number, this quantity, which is a positive quantity, is less than that positive number. This can happen only when that positive quantity is 0. So it implies that m star of I minus L of I is 0 modulus. It implies that m star of I is equal to L of I. Okay. So in the second case, we proved that length of the interval is equal to outer measure of the interval. So we are left with one case when your interval I is unbounded. Okay. So case 3, when I is an unbounded interval, right? So what do you mean by unbounded interval? It means that given any natural number n, howsoever large, okay, I can find an interval, find a bounded interval j with length is equal to, length of j is equal to n, such that j is contained in I. This is the meaning of unbounded interval, because whenever you have a bounded interval, unbounded interval, you can always, given any length, you can find an interval of that length which is contained in your unbounded interval, right? So by monotonicity property, this implies that m star of j is less than is equal to m star of I. Now because j is bounded, so m star of j is nothing but L of j. So it implies that L of j is less than is equal to m star of I. And what is L of j? This is n. So it implies that m star of I is greater than equal to n. It means that given any number, howsoever large, m star of I is greater than that number. So what does it mean? It means that m star of I is infinity. And if your interval I is unbounded, your interval is I is unbounded, though it means that length of I is infinity, right? So in this case also we prove that m star of I is equal to length of I, right? So this was the proof of the theorem that length of the interval is equal to outer measure of the interval. It is a bit longer proof, but it is not that hard, right? So right now where we are, we have defined outer measure, and we have proved three properties for outer measure, right? Our next task is to study the Lebesgue measure. Thank you.